Okay, in the previous class we have seen the magnitude condition and angle condition for a root locus, and we know that we have also defined the root locus as a locus of points which is plotted in S plane with a variation of value of gain k. If the gain k is varying from 0 to infinity, we say that it is direct root locus, and if the gain k is varying from minus infinity to 0, or you can say 0 to minus infinity, it was inverse root locus for us. Okay. Now we have concluded that for our course, root locus means it is direct root locus unless it is specified that it is inverse root locus. So we have seen that with the help of angle condition and magnitude condition, without plotting the actual root locus, we can know whether a given point lie on the root locus or no. For this we have used the angle condition, and after we have found that it satisfies the angle condition, then we use the magnitude condition or that formula for finding the gain k. Correct? So we have already seen this. Now coming to the various rules to construct the root locus. Though it is easy to construct a root locus in MATLAB, you can directly have a command like rlocus and it will construct root locus for you. But there are certain guidelines, because you are not going to exactly plot point by point. So you have to approximate the curve. So for that approximation, we have certain guidelines, or you can say that these are certain rules of plotting root locus. These are not universal rule like that. If I am saying that this particular rule is rule 1 for me, then it is not universal rule that it will be rule 1 for somebody else. Correct? You may find 7 rule or 8 rule or 6 rules depending upon books to books. Correct? So for me, it is rule 1. Before that, one might have confusion that we are working on 1 plus GSH. This means our characteristic equation is 1 plus GSH is equal to 0. So one may ask that where is gain k? Okay, where is gain k which you are varying? So for this I am taking this GS is nothing but k multiplied by g dash s is another transfer function, and this is gain k which you are varying and plotting the root locus. Correct? If gain k is not given, you have to assume that gain k is multiplied with your given transfer function or open loop transfer function. Correct? Okay. So coming to the rule 1. Rule 1 says that whatever may be the root locus, whatever may be your open loop transfer function, it will be symmetrical above the real axis. Correct? Your root locus will be symmetrical above real axis, and this is of course not a magic, but we know that for a realizable system, your characteristic, the coefficients of characteristic equation will be real. It will not be complex, and for real coefficients of characteristic equation, or you can say for real coefficients of characteristic polynomial, its root will be either complex pair or just real. Okay. So suppose it may be have the case, we may have the case like we will have a complex pair, or it may be just a root lie on the real axis. Correct? So whether it may be complex pair or whether it may be a root or you can say or a pole of characteristic equation lie pole of your system lie on the real axis. Okay. So whatever may be the case, this in this side also, whatever may be the case, this value of poles, or you can say this value of roots of characteristic equation are at k is equal to 0. So with the change in value of k, it will move symmetrically. So that's why this root locus is symmetrical about real axis. Why? Because for a real coefficients of characteristic equation, your roots of characteristic equation will be either complex pair or real, and complex pair are itself symmetrical about real axis, and for the various value of k, it will come out to be symmetrical. Rule 2 for me is that the root locus will start from pole and end to the 0. Correct? So when the value of gain k is 0, your root locus will be just a point which is the pole of your system. Okay, pole of your open loop transfer function. Not the system, but the pole of GS edges. Correct? So for the sake of convenience, we are going to assume that capital P is the number of open loop poles of your open loop transfer function, or you can say the number of open loop poles. By saying open loop poles, it is signifies that it is pole of GS multiplied by edges. Correct? Z is the number of open loop 0 and capital N is the number of branches of root locus. Correct? So there might be three cases. When P is greater than Z, means number of open loop poles are greater than number of open loop 0. Second case may be that P is less than Z. Correct? And third case may be P is equal to Z. So we are going to deal these three cases. Accordingly, I have written that case 1 is P is greater than Z. Then whatever may be the greater, whether Z is greater or whether P is greater, you are going to assign that maximum value of, you can say, P and Z. Whatever may be the maximum, you are going to say that it will be equal to the number of branches of the root locus. For example, for case 1, if P is greater than Z, capital N will be equal to P. In second case, if Z is greater than P, capital N will be equal to Z. And in the rarest cases, if it is equal, then of course N is equal to P is equal to Z. So we have just said that root locus will start from poles at k is equal to 0 and n to 0. But when n is suppose n is not equal to p and that is not equal to 0, so what will happen when p will be equal to z? It may be greater or it may be less. So we can say, suppose for case 1, p is greater than z. So I am going to assume that for a special case, p is 3, means open loop transfer function having pole, number of poles is 3. It is not just value of pole, note that it is number of poles. So 3 poles and z is equal to 1. So it is having a 1 0. Correct? So p is equal to 0, 3 and z is equal to 1. Maybe the case like this. I am going to say that it is a hypothetical case I am going to take. So suppose all are on real axis. Correct? So 3 poles, 1, 2, 3 and 1 0. So I have said that your root locus will be started from open loop poles and end to the 0. So it will start for these poles. It is well and good that this pole will start from here and it will end to the 0. But what are the points corresponding to these poles? Means this P minus Z means what? 3 minus 1 is equal to 2. What will be the ending point of root locus for these two poles? So we say that when P is greater than Z, which is actually the most general case. Why it is most general case? Because for a realizable system, the order of denominator is greater than that order of numerator. So this is the most general cases which we will come across while creating the control system. So this is the most general case. P is greater than Z. So when P is greater than Z, so Z number of branches will end to the 0 and P minus Z number of branches of the root locus will end towards infinity, and it will consider for this particular special case that there are presence of two zeros which lie on infinity. Correct? I think my point is clear. In the similar case, when case 2, when suppose for any unrealizable system Z is greater than P, so Z minus P branches will lead to infinity. Okay, how it will go along the along which line it will go to the infinity, we will see. Now, our rule 3 is that we are interested in knowing that whether a particular point on the real axis is a part of root locus or not. What I am talking about is just for the part of real axis, means which part of real axis are actually the part of root locus. For this, the rule says that if the number of poles plus number of zero to the right hand side of that particular section of real axis is equal to odd, then that particular section of real axis will be the part of your root locus. Let us try to understand this particular fact with an example. I have taken an example is that GS is equal to, suppose GSHS is equal to K multiplied by S plus 1, S plus 4, and in denominator it is S multiplied by S plus 3 multiplied by S plus 5. So we are having two zeros and three poles. Poles are at S is equal to 0, then at, suppose it is 1, minus 1, minus 2, minus 3, then at S is equal to minus 3. These are poles. S is equal to 0, S is equal to minus 3, and once again one pole is at S is equal to minus 5. Correct? And zeros are at S is equal to, zeros are at S is equal to minus 1 and at S is equal to you can say minus 4. So now we are interested in that which section. By saying the section, I am going to divide it in the sections. Means beyond this pole, this is one section. This is another section. This is another section. Means whenever we encounter a pole or zero, our section will change. This is another section, and this is another section, and this one is another section. So we are interested in whether this part of this real axis is the part of root locus or not, whether this part is a part of real root locus or not, or whether this part is the part of root locus or not. For this, I have said that take any point on this section which we want to analyze. Suppose I want to analyze that whether a right half of the real axis is a part of root locus or not. So I will take any point, say this is point, and I will take any point on this part, on this section, and find that what is the number of, you can say n dash, what is the number of poles to the right side of this particular point, and what is the number of zero to the right side of this particular point. So of course there is no pole to the right to the point, we'll say P dash is equal to 0, and there is no zero also, so we'll also say that Z dash is equal to 0. So P dash plus Z dash is equal to 0, that is, we are not interested in number, we will say it is even. So the part which are, if P dash plus Z dash is equal to even, that part will be the part of root locus. Correct or wrong? Once again, try to understand with this particular section, means the section of the real axis which lie between S is equal to 0 to S is equal to minus 1. Correct? So for this section, take any point. Suppose this point. So for this point, what is the value of P dash? P dash is 1 because S is equal to 0, pole is there. One pole is there which lies in the right side of this particular section. So P dash is equal to 1. What is the value of Z dash? 0. Z dash is 0. So if you will take the summation, you will say 1, so it is odd. So this part will be the part of root locus. So we will bold this. Correct? Take this section. Any point in this section, P dash is equal to 1, Z dash is equal to 1, 1 plus 1 is equal to 2, that is even. So it will not the part of root locus. This part of the real axis or this section of the real axis will not be the part of our root locus. Take this section, 1 and 1 2 plus 1 3, so this will be the part of root locus. Correct? Take this section, 1 and 1 2, 1 and 1 2, 2 plus 2 is equal to 4 even, so it will not be the part of root locus. Take this section, it will be the part of root locus. So which section of your real axis will be the part of root locus? we can see by this method. So if number of poles in the right hand side of that particular section plus number of 0 in the right hand side of that particular section will come to even number, then it will be the it will not be the part of root locus, and if it is odd, it will be the part of root locus. Whether a occurrence of complex root will going to change this thing or not. Suppose we are having a complex root. So we will not pay any attention to this complex root, because whenever we will cross the real part of this your complex root, this will be always even, because complex root always occur in pairs. So even plus even will be even, odd plus even will be odd. So it is the occurrence of complex root is not going to change the analysis for this particular purpose when we are interested in finding the whether a particular section of real axis is a part of root locus or not. Correct? So we will focus our attention only to those poles and 0 of open loop transfer function which lie on the real axis itself. So this particular concept that if P dash plus Z dash is equal to odd, then that particular section will lie on the root locus is for positive value of K. Please note it that this particular rule is for positive value of K. This is for K greater than 0. Means this is for, we can say, our direct root locus. And if you are interested in the negative value of K, this rule will change. Means for negative value of K, for K less than 0, you will say P dash plus Z dash is equal to even, then it will be the part of root locus. Correct? This is for inverse root locus case. I am discussing it parallel. Correct? Now coming to the rule 4. So I have just specified that generally P is greater than Z because we generally deal with the realizable system, and for realizable system the order of numerator polynomial is less than that of denominator polynomial. That's why P will be greater than Z. So we have also said that P minus Z branches will approach to infinity. Correct? In this particular case. So how these branches will approach towards infinity? We will take the help of asymptotes, concept of asymptotes. You might have remembered from your class 12 concept that for rectangular hyperbola, this is your graph of rectangular hyperbola, we said that this line is asymptote to this graph, to this curve. Why? Because the concept of asymptote says that this curve will approach towards infinity along this line. That's why this line is asymptote to the curve. These asymptotes are a straight line along which the curve moves. Any curve, it may be any curve, along which the curve moves when a particular value of that curve changes to infinity. Correct? So here we are also going to discuss the asymptotes. Means what will be the asymptotes. So angle of asymptotes, these all angles, this theta, okay, this theta is the angle of asymptote. It is measured in the positive with respect to the positive direction of sigma axis, or you can say the angle is measured with the positive direction of real axis. Correct? So I have given the angle theta is equal to 2q plus 1 multiplied by 180 degree divided by P minus Z, where Q starts from 0, 1, 2, 3 up to P minus Z minus 1. Correct? Suppose we are having a hypothetical case we are going to take. We are having 3 poles. P is equal to 3 and once again, P is equal to 3 and once again Z is equal to 1. Correct? Similar example I am taking. We will solve one complete numerical, then the case will be clear more. Okay? So this will end here. So how many asymptotes will be possible for this? P minus Z. Note that value of Q is going to P minus Z minus 1. So we are having what theta is equal to 2Q plus 1 multiplied by 180 degree divided by P minus Z. Correct? So P minus Z is 2. So you can say 2q plus 1 multiplied by 90 degree for this particular example. Put the value of and p minus z minus 1 is equal to what? 3 minus 1 minus 1 will be equal to what? 1. So put the value of q is equal to 0 and value of q is equal to 1. When you will put the value of q is equal to 0, you will get theta 1 will be equal to 90 degree for q is equal to 0. When you will put the value of q that is equal to 1, you will get theta 2 will be equal to what? 270 degree at q is equal to. Correct? So we don't know what is the breakaway point. We will later discuss, but this will start from this pole, this will start from this pole. Where they will approach, one will turn directly this along this line. This is 90 degree, and this will another one will turn towards 270 degree. Correct? And this is not asymptote because a 0 is available. Correct? So I hope my point is clear. It will be more clear when we will take a complete numerical in the next class. Please come with the graphs. Correct? Okay. Now once again this angle of asymptotes is for positive value of k. Means it is for direct root locus. And when we will talk about the angle of asymptote for inverse root locus, this is for k greater than 0. Then this angle will become 2q multiplied by 180 degree divided by p minus z for inverse root locus. Means when the value of k will 0 to minus 1. This is for inverse root locus. This is I am telling for computation point of view. Okay? Well, now coming to the rule 5. So we have just seen that our root locus when is going to approach towards infinity. Okay, so it is going to break at some point. Means one branch will move in some other direction and another will move in some another direction. So what is that point? Means that particular points which lie on the root locus and which is at which the all the asymptotes will merge. Correct? So it is the location of asymptotes on real axis. Means we are interested in finding the intersection points of asymptotes on the real axis. This intersection formula, that is, this is the value of sigma, is directly given by summation of real part of poles of GSHs minus summation of real part of zeros of GSHs divided by P minus Z. Correct? In some literature, you may also find that this is they will not directly read that the real part of pole of GSHs. Rather, they will write that summation of poles of GSHs minus summation of zeros of GSHs divided by P minus Z. I am avoiding that more calculation with the help of this formula, that we are going to consider the real part only. Why? Because if there will be complex root or complex pole, then it will occur in pair and the imaginary part will cancel each other. So why to pay attention to that imaginary part which is ultimately going to be cancelled. Correct? So for sigma will be equal to real part of poles of GSHs minus summation of real part of zeros of GSHs divided by P minus Z will be the intersection point or the point at which all the asymptotes will intersect. So please note that it is not necessary that this intersection point will lie on the root locus. It may or may not lie on the root locus, because that intersection point and the corresponding section may or may not be the part of root locus according to the rule number 3. Correct? Okay. Now coming to the next rule, that is rule number 6. We will take a break of 2 minutes.